Hi folks, and welcome back to Fermi Physics Solutions. This is the third video in the series of concept explainers looking at the behavior of current in an electric circuit. This video is going to look at visualizations to understand how current flows in series circuits and parallel circuits. So the most basic circuit you can make would involve one battery, one component, and the wiring you need just to set up a closed circuit. So in this case, I'm just going to use a resistor, which is represented by the little rectangle at the bottom. You could also use something like a bulb, which will light up in this circuit, or a buzzer, which will give off sound in this circuit instead. And as we know, this is a closed circuit, so we're just going to take a quick snapshot of those charges moving around the circuit at any given instant. And remember, this represents how many charges are passing through a point in 1 second in this diagram. The little loops represent a little point on the circuit. And we can see if we look around the diagram, and I've highlighted two of them, but if we kind of look at the shapes of all the charges, there's 3 coulombs passing every point per second. So again, this diagram works off the assumption that every particle drawn has a charge of 1 coulomb. Again, that's not accurate in real life, but just for the sake of the diagram and explaining it makes it a lot easier to think of it like that. So here we have 3 coulombs passing per second. On the left hand side just before the current goes through the component, but also on the right hand side when it comes out of the component back to the battery. And while we can't see inside it, there's also 3 coulombs per second passing through the battery. Again, that's not what we measure in real life. What we would measure is using ammeters. So here I can see that I have 3 amps of current flowing at every single point in the circuit, and we call this the constant current model, where there is a constant current flowing out of the battery, down the wire, through the resistor, up the wire again, and then through the battery. So if I add a component in series, I take a quick snapshot of the charges at any moment in time, I can see the setup now looks a little bit like this. And if I look at the diagram, I should be able to see that those charges look a little bit more spaced out than usual. So I'm going to draw my little loops on them. And if I look at the loops there, I can see that this diagram represents that I have less current now because there's only 2 coulombs per second passing through each one of those loops. So that tells me at any point there is only 2 coulombs per second, which is 2 amps flowing around the circuit. Why does this happen? Well, let's look at our battery. The battery has a fixed potential difference. When you buy a battery, it's 1.5 volts, 3 volts, 4.5, 9 volts, depending on the battery you get. But now there is more resistance in this circuit because we put 2 resistors in series where it's one straight after the other. So you have a fixed amount of potential difference trying to push current through more resistance now. And if the resistance is after going up, but what you're using to push the current is the same, then something has to give, and that means your current is going to drop. So the battery can't push as much current around the circuit anymore because there's more resistance there to try and push through. So again, we'll represent this using an actual ammeter, and here we can see that I have 2 amps. So in this particular case, I have now dropped my current in this diagram. So I have increased my resistance, and I'm using the same potential difference, which means I'm after decreasing my current. Again, if I look at this diagram here in the same way again, what I can see is that I have 3 resistors in series. And again, that means I have the same battery. The same battery is trying to push current through now a higher resistance again. So it's got the same push, but you've got a higher resistance. Something's going to have to give, and that means the current is going to drop in this case. So the diagram represents that by the charges are more spaced out. But what that means to us is that you have 1 coulomb of charge passing all those points per second. And again, following my constant current model, that means I have 1 amp before all the resistors, 1 amp after going through the first, 1 amp after going through the second, 1 amp after going through all of them, and 1 amp going back through the battery. So the key thing here, you're always using the same battery in these setups. So as you increase the resistance by putting more resistors in series, your current is going to have to drop in order to kind of balance that out. And whatever change you make in your resistance, that change is going to be the same type of drop in your current. For instance, if you double the resistance in your circuit, your current is going to drop by a half. If you triple the resistance in your circuit, your current is going to drop by 1/3. So, those changes balance each other out that way as well. Now, parallel circuits work slightly differently, so because the setups are different as well. So we're going to go back to this original setup, and if we look at the original setup here, we can see that the current flows out through the positive, down through the resistor, and then up again through the negative. So in this case, we can see there are 3 coulombs per charge passing through that resistor. So let's just say that's a 1.5 volt battery, and that resistor is half an ohm. Then what you're going to end up with is your 3 ohms of resistance going, sorry, your 3 amps of current going around that. So if I look at those numbers there, I can see that I have 3 amps and 3 amps. Now, so when I look at this circuit here, this is what we call a parallel circuit, and I'm just going to show the most simplest version we have, where we have what are called 2 branches. So here the wire comes out the positive terminal of the battery. At this point here where the wire splits, we'll call that a junction. And the first branch to come off that junction goes, as we can see, straight across horizontally to the right to the next junction here where the wires come back. The second branch goes down and then to the right here and connects back here at this junction as well. So this is the first branch, this is the second branch. At this point, they come all the way back to the negative terminal of the battery. So what I'm going to ask you to do quick is I want you to just ignore this little branch down here. So imagine that this is just a 1 branch circuit with the wire going here down into this resistor here, going all the way back up. So if this is my 1.5 volt battery and this is half an ohm resistor, then we know from looking at the video earlier, that's going to be 3 amps of current flowing from the positive here through this resistor and then back up here. So we know that there should be 3 amps of current going through that resistor. Now what we're going to do is we're just going to ignore this little branch here. We're going to pretend the circuit is, again, just a single branch circuit where it goes out the positive, down through this resistor here, all the way back up. So we're ignoring this branch. And if we do that, we have 1.5 volts here, we have half an ohm here. So we know from looking at our previous circuits that that should be 3 amps going through that one there. So we should have 3 amps going through each of them. And let's have a look at that now when we see the charges. And when I see the charges and I do my little snapshot as they move around the circuit, we can see that within the first branch, there is 3 amps of current passing the center point of this loop, which means there's 3 amps going through this particular branch. There's also 3 amps of current going through the center point of this loop, which means there's 3 amps going through that resistor as well. So what is notable here is that the current coming out of the battery at the center point of this loop does not equal the current there and the current there. And what we notice here is that the current at the center point of this loop is 6 coulombs per second, or 6 amps. So what we can see here is what's actually happening is the current is splitting as it goes around the circuit. So because I have 2 separate branches which are behaving like 2 separate circuits, I actually get 6 amps of current drawn out of my battery. The 6 amps comes down to this junction, and at this junction it splits. 3 amps goes to the right hand side through the first resistor, 3 amps goes down to the right hand side through the second resistor. So you have 3 amps and 3 amps going all the way through until you get to this point here, in which case the 3 amps and 3 ions combine together again to give you 6 amps going all the way back up and back into the battery, and then 6 amps through my battery. Since there's more current being drawn from the battery for the same voltage that the battery has, that's going to expel your battery quicker, and you would run out of your battery would die before, or die quicker than it would in a circuit where there's only 1 resistor set up in a single loop. Another thing to note here, that I made this so that this resistor and this resistor are identical, which is why you're getting an even split of 3 and 3. But you can get any combination. It could have been 2 and 4, it could have been 1 and 5. It doesn't even have to be whole numbers. You could get 0.5 of an amp going this way, and you can get 5.5 of an amp going this way. What does matter is that you have 6 amps going into this junction, which means 6 amps have to go out the combination of the two together. And if 6 amps are going out of this junction back into the circuit, then that means whatever goes to the right along this line and vertically up this line, when they meet at this point, they also have to combine to 6. And again, if I think about this, it's a 1.5 volt battery. There is now 6 amps of current. And if I compare that to my last slide where I had 3 amps of current, what that tells me then is that if my potential difference of my battery stays the same and my current rises, well, something has to give. And what gives is that the overall resistance of my circuit is actually after going down. So by placing the two resistors in parallel, the resistance has gone down of the overall circuit, and that's balanced off with the increase of current drawn from the battery. But again, as I've always said before, we don't look at circuits and look at the charges as they move. So if we place the ammeters where we would have shown those loops, we can see there are 6 amps of current going here. There are 6 amps of current going back into the negative terminal. And at this point here, there is a split. In this case, it's 3 to the right into the first branch, 3 down into the second branch. But as long as these two numbers add up to the 6 amps, then that's going to show me that my current is splitting between the two branches.